All right, welcome to my talk, Hack in Your Sleep, or How to Hack in Your Sleep. I'm David Hunt. I go by Private Ducky in most of my online profiles. You can find me on Twitter if you want to look me up there and get in contact. I also blog a lot at feed.prelude.org, so you can also find me there along with a lot of things that are just generally on my mind. So today, what we're going to be talking about is the concept of automated red team operations, automated penetration testing, the concept of how do you take offensive security, which has traditionally been a manual only exercise, and how do you start to incorporate automation, hence hacking your sleep, and how do you incorporate that automation to leverage your time better. So instead of manually testing port scans, we typically pull out Python and Nmap and we create our own port scanning utilities to automate that process. So how do we take that a step further and start doing offensive security in a fully automated way so we can spend our manual effort, if we have a red team or we have access to a red team, we can spend that manual effort doing more complicated, interesting, creative red team operations instead of burning our time on the more mundane, automatable aspects. So who am I? I'm the CTO here at Prelude Research. I focus heavily on automated red team technology, so that's making red team technology more accessible to more people. I came out of MITRE, where I spent the last couple of years, where I was building the MITRE Caldera framework. So I designed the second version of that, version 2.0 and up. And in building that framework, I got a kind of a first-hand look or first glance at how the breach and simulation industry is set up, how the different tools that deal with automation are succeeding, where they're failing, kind of where the concepts are kind of headed. And that's where a lot of the work I'm doing now at Prelude is essentially birthed out of. Over the last 12 or 15 years, I've spent time at a number of different organizations, such as Rockwell Collins as an operator, such as John Deere, where I spent time in software engineering and big data, a few years at FireEye, where I worked within the red team and threat intelligence spaces, and then disconnected years at different startups in the security side and consulting for agencies and other types of work. If you were to say, what do I do in a nutshell? I build autonomous systems which can hack into computers. I spend a lot of time designing systems and technologies and processes that are built to make the whole red team process, the whole offensive security process, more accessible. In today's world, that means I am working on Operator a lot. So Operator is a free, largely open source, autonomous C2 command and control framework that really tries to fight semantics, complexity, and technology and replace it with a simplistic approach to offensive security and trying to bring the concept of red teaming down to regular boots on the ground users who don't need to burn time trying to figure out semantically what they should be doing, but instead should be focused on securing their organizations. All right, what should you learn today? Now, we're going to go through a few different concepts. The first is, how do you think like a human? You may think you already know because you are a human if you're listening to this conversation. But we're going to go through how you actually think. We're going to break that process down. We're then going to convert that human think into programmatic reasoning. How would a computer do the same process of decision making and thinking that you do? Then we're going to overlay that by thinking like a malicious actor. Then we're going to build a programmatic, repeatable adversary that uses this knowledge so we can actually put that good knowledge to practice. And then we're going to apply the knowledge from this hour to immediately improve your security posture by actually hacking in your sleep. So we're going to design an adversary profile at the very end that will kind of complete the circle. All right, going into this conversation, what are my assumptions? You probably know a thing or two about red teaming. It's a security conference after all. You likely work in security, offense, defense, purple team, IT, InfoSec, a lot of different concepts here. You're interested in performing red team assessments to secure something or to test if some defense is or is not working. So my assumptions are these are probably in the ballpark of who you are as a professional, and we're going to go with that as we continue. Okay, let's focus on how do you make decisions as a human. So what you see, I'm going to give you a second to kind of consume this information on screen. What you see on screen are a collection of decisions that are possible. So let's say these are your full extent of abilities. You can do these, I don't know, 10 or so things. Now, left to right is going to represent our chain of decisions. We start off on the left, we want to end up on the right. Let's say, for example, we want to drive to work today. That's our goal, is to drive to work. So we're starting in the wake up state. So imagine each one of these columns, if you will, is a state. So we're going to start off waking up. Now we have three decisions in front of us. We can eat breakfast, we can walk the dog, we can hit snooze. Now, you'll notice that walk the dog is highlighted red. The reason that is highlighted red is because we cannot immediately wake up and walk the dog. That is because it has a dependency. That dependency is that I need to put clothes on. In the third column, the third state, I must put clothes on before I could walk the dog, so I cannot do that as a decision. That limits me now down to two decisions I can make. We'll start off and we'll hit snooze. Okay, so hitting snooze, that is a valid decision. However, I'm at the end of the road. I cannot move from here to achieve my goal, given my set of abilities, to drive to work. So that's a no-go. Going back to the beginning, I will eat breakfast. Okay, maybe I can eat breakfast and there's something actionable I can do after that. So maybe after eating breakfast, I put clothes on. Okay, so now I'm making my way through the decision chain in order to proceed. So once I put clothes on, I can now walk the dog. That prior dependency has now been unlocked. After walking the dog, I may decide I want to go for a run. This opened up a handful of new potential unlocked abilities at this point, but going for a run does not get me closer to driving to work, therefore, bad decision. So maybe instead, after I walk the dog, I can skip over putting clothes on. I already did that. And I can get in the car. Once I get in the car, I could have chosen getting on a bike. I could have chosen uh, going for a run, although I already did that one. So once I go and jump in the car, I can drive to work. I could have driven to the circus, but I chose to do the right thing, drive to work, and happy. I made it from state 1 to state 5 and achieved my goal by carefully deciding according to the abilities I had and chaining them together in a way that achieved my goal. Okay, decision logic, thinking in a linear way. In order to break down how I thought through the prior process, how I got from state 1 to state 5, I first had to identify what is my goal. Once I understood my goal, what is the set of abilities that I contain? Your set of abilities may or may not achieve your goal. You may or may not have that capacity. So once you understand your abilities, what preconditions exist for each one of your abilities? Walking the dog, as we saw, had one. Do you have any overlaps in your ability set? Can multiple things essentially achieve the same goal? And then your last and final most complicated thing is which ability should I choose? And that kind of goes in tandem with in what order. So when we looked at the prior step, we could identify what is my goal. I wanted to go to work. What are my abilities? Here's a handful of them. These are the things that I know how to do. What preconditions did I have? Well, walking the dog required me to put on clothes. And then do I have any overlaps? Yeah, getting in the car, getting on a bike would have achieved the same thing, mode of transportation. I chose getting in the car. That's an optimization, probably on time. But I could have achieved that through getting on a bike. Next, understanding finite state machines. Yes, this is math. Finite state machines is a math concept. Now, what you're going to see on the screen here looks complicated, but it's actually quite simple. So if we've ever been to a subway, in a big city, you probably see in the top right here these turnstiles. Now, what you see in the main picture on the screen are the different states that turnstile could be in based on actions of people going through or not going through them. So we're going to start off in the locked state. So you see that big circle there on the left hand side, that is the locked state. Now, when you put a coin in, you can follow the arrow and it jumps over to the unlocked state. So when you enter the unlocked state, if a coin is being put into the turnstile, you remain in the unlocked state. Otherwise, you push through the unlocked state back to the locked state where you can push it again after putting a coin in and enter the unlocked state. So this is a very simplistic way of how a coin, an unlocked state, and a locked state work together in order to transition the user, the person going through, into different states. Now, how would that sort of process the concept of states overlay on top of making human decisions? We'll call this version 2. You've got 5 states as split up by these different columns. States 1, 2, 3, 4, and 5. Now, as we transition from one state to the next, we get there by making a decision that puts us squarely in one state at a time. That's where the finite state machine comes in. Once we're in that state, there are decisions we can make to move from one state to the other, but those have repercussions such as unlocking a dependency, or they may restrict what my decision is in the next state that I get to. So each state comes with different opportunities to myself. You might say, wait, isn't this talk about security? Why are we talking about human decisions and turnstiles and finite state machines? Yes, so on the security side, this should hopefully be building the blocks, the foundation for thinking about how an adversary makes decisions. So what I have on screen is something that probably everybody is aware of and familiar with, the attack matrix. Spanning across the top columns here, you can see the different tactics that are available within the attack matrix. So you've got things like initial access, discovery, lateral movement, execution. These are the tactical decisions an adversary could make. We can call these, if we want, states. Down on the rows, we can see the techniques. Now, let's look at credential access as a tactic. You have brute force. That is a technique. That is a subset of how to perform credential access. You could brute force credentials. You could input capture for credentials. You could sniff the network for credentials. These are your techniques that you could do. Now, what isn't shown on this matrix are the procedures, the P and TTPs, tactics, techniques, and procedures. Procedures are the variations of the techniques, the implementations of the techniques that you could actually execute on target. So an example of that, how would you brute force credentials? Well, you might grab a password list off the internet and execute 1 billion passwords against a system. There might be thousands of different commands from PowerShell to Bash to Python to assembly that you could write in order to attempt that technique. And that is the attack matrix from that 10,000-foot view. Breaking it down further, especially as we kind of overlay this concept on top of the human decision making we talked about prior, we are now going to introduce the cyber kill chain. Now, off to the right hand side, you can see familiar tactics from the prior screen and familiar technique IDs. And so a tactic would be something like persistence. Under persistence, you'll have techniques. A technique in this case, T1037. That's a technique under persistence. Now, the procedure is the actual implementation. And so this is a specific persistence attack that you could do under T1037, which is under persistence. Now, you've got a number of tactics. Each tactic has a number of techniques. Each technique has a larger number of procedures. Now, the cyber kill chain was originally developed by Lockheed Martin, and this is a model that identifies what adversaries must do or usually do to complete in order to achieve an objective. And so the Lockheed model, the cyber kill chain, has 7 different steps that a threat analyst can use in order to identify an adversary, identify compromise, to attribute an attack to a specific adversary. So it is the behavior that an adversary takes, the decisions they make, their immutable behavior inside of an environment is what the cyber kill chain attempts to map. Now, this is very similar to the MITRE attack framework in a concept that they are classification systems. So the MITRE attack matrix, which we showed on the prior screen, is curated knowledge base and model for cyber adversary behavior. Now, very similar, there's a lot more tactics, there's a lot more techniques. It is a more fine-grained or closer view than what we see in the cyber kill chain, but they both achieve a similar goal, which is to act as a classification system for threat intelligence analysts to talk about attacks. So let's harbor on this for a minute. So a cyber classification system offers you a couple different benefits from the intelligence, the CTI, cyber threat intelligence point of view. So the first one is common language to describe an attack. So in order to describe how an adversary is attacking a system, you need a way to map their behaviors and tools and processes to something. And that common language is great to use attack, the cyber kill chain, and so forth. It also maps attacks back to something. So because an attack can be so varied and creative, you need the ability as a cyber threat intelligence analyst to map that behavior back to something in order to loop back into the common language. Let's take a look at how an attack may unfold, specifically as we overlay it with things like classification systems. So we'll say we have a cyber threat intelligence analyst out here in Los Angeles. At the same time, we have an adversary over here somewhere in Asia. Now, the adversary may attempt to attack New York, and maybe they do it from an IP address 1234. We'll say that is an Asian IP address that is known to come from a IP vendor out in Asia somewhere, and that is a known IP. Now, when they attack New York with that specific IP address, the threat intelligence analysts might notice that and say, ooh, that IP address is bad. That is known as an indicator of compromise, an objective truth about a computer system that an adversary may be using or leveraging to complete an attack. And so the analyst will say, oh, IP address 1234, bad, we will start blocking that from now on. So now the adversary needs to go back to the beginning and say, well, maybe I will proxy my connection through South America and still attack New York, but now my IP address is going to appear it's 5678. Well, that's another approach, right? So now it's a cat and mouse game. So the analyst can look at the IP address 5678 and say, oh, this is a known bad IP address coming out of South America through one of their vendors. We will block that IP address and continue on. Now, cat and mouse game, the adversary can cycle through many, many different types of IP addresses and proxy their connection and continue to stay one step ahead of the adversary. So now we'll flip over and say, okay, well, maybe the analyst can't use indicators of compromise such as IP addresses. Maybe they need to look at the behavior. The cyber kill chain, the MITRE attack framework, they need to look at the immutable behavior of the adversary. So maybe the adversary attacks New York again, and the threat intelligence analyst starts looking at the techniques that the adversary is using to conduct the attack. T1005, T1010, T1113, right? So now the analyst is saying, okay, well, when I see these 3 techniques completed in tandem, I know that this attack is both malicious and attributed to this threat actor out in Asia. Now, at the same time, an adversary may pop up in Paris, read a threat intelligence report about this Asian threat actor, and say, oh man, everybody thinks that these three techniques are going to be attributed to them. So I'm also going to attack New York, and I'm also going to replicate and copy these three behaviors in order for the analyst in Los Angeles to think that the threat actor in Asia is attacking New York, but it's really, in fact, me in Paris. And so this is a very big problem in the threat intelligence space, and why attribution is such a tricky game and such an important game, and it takes a long time to conduct, but it is also a insight into how analysts need to leverage both indicators of compromise as well as behaviors in order to determine who did what, how they did it, and have a level of confidence in that attribution. On the topic of indicators of compromise, we talked about IP address in the prior slide. Now, there's a variety of other indicators of compromise, such as file paths, network ports, fully qualified domain names, usernames, passwords, email addresses. Probably the most popular, file hashes, things like MD5, SHA-1s, 256s of files themselves that are known to be malicious. Pulling out a couple in specific, we'll look at IP address. So these different indicators of compromise can have some issues. So for an IP address, who owned it at the time of compromise? IP addresses are sold in batches, and who owns a specific IP address based on the dynamic nature of IPs may change this month to next month. So time is a factor in how do you determine who owned an IP. Username and passwords. If you were looking at arbitrary text, how would you be able to determine as an analyst what a password is versus just a plain old string? Because a password is essentially a string. There may be some specific rules in an environment, such as it needs to be 12 characters. It needs to have a special character at the beginning and a capital letter and a lowercase letter, but they're still strings, they're words, they're alphanumeric characters. Now, identifying as an analyst what is a password versus just a word can be difficult, but then understanding that it takes more than just a password in order to leverage, say, an attack on a, say, an initial access or a lateral movement, you likely need a username as well. And so connecting a username to a password in order to identify that these go together and these are used together can be a challenge within the indicator of compromise space. Okay, let's circle back to how an adversary is going to make a decision. So we've learned a lot so far, hopefully, about classification systems, their pros, their cons, and we're going to leverage right now the MITRE attack system in order to talk about behaviors. So let's say an adversary drops an implant and gains a foothold on a target network. Let's say that they have 6 different tactics or decisions that they could make. So they could run discovery, collection, impact, exfiltration of data, lateral movement, or privilege escalation. So as an adversary, maybe the first thing I want to do is hop in and collect data. There's something I want to collect off the system. So I make a decision and I say I'm going to hop into collection. And then from collection, there are 2 different options, 1560 and 1123 on page, that I could choose. And that will be kind of the subset, the technique level. And I say I want to do 1123. So out of 1123, my next action, my procedure is to capture the audio. And so I look into my database of TTPs, the commands that come out of my head or that I have written down on my scratch pad, and I say, well, what can I do to capture audio? I need to install an audio recording package on a Mac OS, so SOX is a popular one out of Brew, and I am going to install it real quick, and then I'm going to record 30 seconds of audio and dump it to a recording.wave file. And that would be my process for just a quick and dirty, how do I make a decision? How do I navigate a classification system in order to pull out the actual command out of my head or out of paper that I want to execute? All right, now how do we take that knowledge and hack computers? Now, we're going to say we have an adversary sitting behind a command and control center. That adversary has access to a TTP database. This is their full collection of things they know how to do, all the attacks that they understand. They also have footholds on 5 different target systems in a network. So they've been able to drop rats that are connecting back to their command and control center. So this is the adversary's starting off space. Going back to how to make human decisions, we need to identify our goal first. So we'll say that our goal is to steal important files. So we want to identify the important files and then figure out a way to exfiltrate them to steal them. That's our goal. The first thing we're going to try is we need to find the important files. So this could vary from system to system, especially based on the target, but I need to have a way to identify what is important and what is not important. Then I need to create a staging directory. I need to make a directory on my target systems in order to stage my important files. So I want to copy the important files from around the systems and drop them into a single place, ideally on a network share if I can do so, and just have a single spot. Then I'm going to compress the staging directory. I want to do that because I want to make it as small as possible, and instead of exfiltrating dozens or hundreds of files over the system, I want to compress down to a small size and exfiltrate a single compressed directory. And that leads me to my last thing that I need to do, which is to actually exfiltrate the compressed directory. This is how do I get it off of the target network and into my own computer and back into my command and control center. The challenge of these steps when we're looking at this from a fully automated way is how do we take the arbitrary text output of each of these commands, each of these steps, and use it to create the input for the next decision. So how do I, once I find important files, how do I dynamically take that information and lead it into staging files? Well, that's what we're going to look at now. We're going to try to solve that challenge. So the very first command, I need to find important files on the system. We are going to say this is a command that could do so. If you're familiar with Bash, this might be easier to read. We want to find all of the files inside these 3 user directories, downloads, desktop, and documents, type as file, and we want to find those that have been modified in the last 1 day. Why 1 day? In my personal experience as a red teamer, I've noticed that important files tend to be modified on a semi-regular basis, so I will look for things that have been modified recently in order to determine importance. Now, let's say I run this command on instruct my rats to run this command on my target systems, and this leads me to finding 3 different files. They're in 3 different directories. They have 3 different names, and they're of 3 different file types. Now, this is information that I did not know before, so I couldn't predict or hard code the results of these, so I have to work with what I get dynamically. So understanding that I got these 3, I may have a second command that will copy files that I find into my new directory. So we'll say that I have a stage directory already on the target system, and notice this command when I do the copy. It is a hashtag curly braces with a variable inside, file.t1005. Now break this into the 2 parts to eliminate on the period here. The file is the indicator of compromise. In this case, it's a file. It is a actual file path that I'm looking for. And then the right side of this period is the technique that it comes from. Now, the first command I ran to find important files is classified under the MITRE ATT&CK framework as technique T1005. And so what I'm saying in the second command is I want to fill this variable in automatically with any file that was found by running T1005. So this allows me to not care or not know or predict what the first command is going to output, because the second command will be able to consume that output and fill in the variable. Now, copying this file, this command is actually broken down based on my prior result into 3 distinct commands. And it's going to copy each file that was found into my directory. This is how we can dynamically create the adversary behavior and create chains of commands together by feeding the output of one to the input of others. Now let's look at this in practice. We're going to jump out of the slide deck, hop into an actual environment, and see if we can replicate a privilege escalation attack and an adversary mindset. All right, now here in the real world, we have an environment with a command and control center up and running. Within the command and control center, we have a single agent, ColdDuck, connected from the target system into my command and control. Now I can click into it. I can see that ColdDuck has not done anything interesting, but I can see that it's got no procedures executed. It's not currently doing anything, so it's just kind of there beaconing back. Now I already have an adversary built called I want root. Now what I can do, I'm going to go ahead and edit the TTPs. And I can see that I have 3 TTPs associated to ImRoot. Now the first one, spawning a root agent. So this one will start a new agent on the target system as the root pseudo user. So I can see here it's a privilege escalation T1078 classified procedure. Scrolling down, I can see that it would work on a Mac OS. It's a bash script, and I can see right here that it will attempt to echo a found password from a T1010.001, the sub technique. From one of those, the output of that type of technique is the password we'll use, and we're going to pipe that password into a sudo command, which will attempt to start a new agent that is running as that root user. And that should come in as the name of the computer -root. The second procedure this adversary contains is the password right? This is a credential access tactic T1110.001, and this is password guessing. So we can see right here it is going to attempt to use a password found from a T1552 procedure, and is going to attempt to use that found password to see, does it work, does it not work? If it works, it's going to echo out the password to console. Now this password, because it's coming from an 1110 procedure, we can see here could fit in to this location. Going down further, we can see another credential access tactic. This one is a T1552. This one is credentials and files. So this is a procedure that will attempt to find every file that has the phrase pass in the file name. For each one, it will check against the popular RockU text file. It says billions of passwords that have come from different types of password dumps. If you use Kali Linux, this is dropped on there by default as a password list. And so what we're doing is we're saying, can we match up any password from the files that have PASS in the file name? Can we match up all of the names in those, all the words in those files to the popular RockU password dump? And can we filter that down into a actual potential password list, things that we think might be passwords on the computer? And that will output password.1552 variables. So if we look at this backwards now, we are going to attempt to run the password finder first, which will filter down potential passwords on the computer. This will link anything potentially found into this next procedure, where this variable will get filled in from the 1552 prior. Now executing this, which is checking if a given password from the filtered list is right or wrong. If they are right, it will chain into this final command, which will attempt to spawn a new agent that is running as sudo on the machine. Okay, now let's take this for a spin. So we'll close this, and we will click deploy. Now we can see the agent running quickly here. It is currently running the commands as executed, And we can see now we got quickly a root beacon. Clicking into the root beacon, we can see it has done nothing. It is currently just in a beaconing state. Clicking into my original agent, I can see that it has now done a number of things. As I scroll down, I can look at the first thing. It did a RockU password finder. Now I can see here it executed the command as I saw before, and it is looking for passwords from my local disk. It found 4 potential passwords. These are passwords from my own files that happen to match the passwords from the RockU text file. Next, it used each one of the passwords to attempt to see if it was correct on the given computer. So I'm scrolling through and looking. This one it tried David. And here we go. So we can see this one succeeded, Golden Goose. So it executed this command and it spat out a password called Golden Goose. Now as I scroll past the other password attempts, I can look at the command that is currently executing, because this is the command that is holding my root agent open. I can see that I echoed out the Golden Goose found password, and I'm echoing that into a piped command, which is starting a new agent that is now running as the root user. So this command is running and holding that open. So now I have 2 beacons that I'm capable of using. I can discard this if I want to close my agent off, but now I was capable of fully chaining a privilege escalation on a Mac from one non-root agent into a root agent. Okay, now I removed the original agent, and we're now just looking at the root. Let's go back to the slide deck where we did the finding of important files, the staging of important files, all the way through the exfiltration. Let's go ahead and see if we can replicate that in a real world environment. So I'm going to start by clicking to add an adversary. Next, I'm going to give it a name. We'll say file thief. File thief. And we will add TTPs. Okay, so as I'm looking to create a chained adversary, I'm going to first filter down to crown jewel related TTPs. This will at least filter down what I want to do. So as I scroll down, we'll look first for finding recent files. So let me see if I can search for that. Perfect. So when I look at this TTP, I can see the command I used on the slide deck for finding files within the last day, modified within the last day. Now I can see a similar one on Linux and a similar command on Windows for PowerShell. We will go ahead and add this TTP to our adversary. Next, we will look for the creation of a staging directory. So scrolling through TTPs, I can see creating of a staging directory with commands that will work again on all 3 operating systems. So I can see here I am making directories and I am echoing out back to console the name of the directory. The reason for the echoing out is so I can capture the variable from 1074 that there is a directory, an indicator of compromise, that the next stage, that the next dependency can be unlocked, which as I scroll up, I can see that we have that TTP. So staging collected files, I'll give this to my adversary as well. And I can see that one of its dependencies is a directory.t74. This means, thinking back to the slide deck, that my adversary requires the output of a T1074 that is a directory indicator of compromise in order to fill this variable in. This is why I echo it to console in this prior step. Next, I need to find a compress for my stage directory. So I can see that right here. Again, all three operating systems are present, and I can see different commands for compressing the archive. And similar to the creation of the directory, I can see after I tar up this directory, I echo it back to console to essentially tell my adversary that, hey, here's a new variable you should look for. And finally, we will need to exfiltrate this directory. So scrolling through, I can see that I have a file.io exfil. This, again, works on all three operating systems. I will add this. Now, I can see that this is going to use the popular one-use only file serve called file.io. There are many like it. And what it will do is it will take the exfiltrated, or sorry, it will take the compressed directory, my staging directory, and it will curl that to file.io. Now, this will give me something that, as an adversary, I can now navigate to the output URL that this command will create, and I can simply download my compressed directory. So we'll close this, and we will deploy our file thief. Now we can see it off here and running. It is executing. It has things queued. I will click into it, and I can see it working. So what I will do is I will scroll down quite a bit and see the very first thing it did was attempt to find recent files. Opening that command up, I can see that it located quite a few. So 7 or 8 different files, and including some of the video clips that I'm using for this particular recording. And I can see here the arbitrary text, which is this output, was parsed automatically and broken down into indicators such as file and the technique that came, say T1005, and I can see what they look like. Scrolling down further, I can see the different procedures that are available to me if I want to chain the output of this command to the input of others. So I can see T1074, 1486, and so forth. The next command, I can see I created a new directory. And I can see here the same deal. It parsed results, and it parsed out that a file T1074 was in this location as well as a directory. Now, as a human, I can look at this and say, well, that's a directory, not a file. So I'm going to go ahead and remove the file. That's a directory. Now, what could an adversary chain to this result? Well, they could chain a creating of a crypto key. They could compress the directory. They could stage. There's a lot of things an adversary could actually do once they're capable of creating that directory. Finally, we are rolling through the staging process. We are going to take all of the files. You can see this used to be a variable. All of the files that I found from the first step, finding recent files, and moving them, copying them, sorry, into the newly created stage directory. So I can scroll up and see a number of these files being staged. As I move up a little bit further, I can finally see a compressed stage directory step. Clicking into that, very similar to creating the stage directory in general, I echo out my tar gz, and I can see I was able to parse it, and I can see that there are 2 steps that I could do in order to exfiltrate. I could upload the file to a target system over a custom HTTP endpoint, or I could do what I actually chose to do in this adversary, which is to leverage a file share to exfiltrate the directory. Finally, as I move up, I can see that the file.io step failed. Now this one's interesting, right? So I can see that the adversary was blocked through the stage, or through the attempt of exfiltrating the commands or exfiltrating the compressed directory. Now I can see command timed out. Well, this is something that is great to know from both the offensive and defensive standpoints. Why would it time out? Probably because the files it attempted to exfiltrate were massive. They were video files, multiple gigabytes, and they probably could not be handled by file.io. It timed out. Now, that is something an adversary could then circle back to, knowing that this step failed and attempting to filter down those important files down to a certain size, maybe, or attempting a different route in terms of exfiltration. Maybe I should have chosen that custom HTTP option when it came to exfiltrating. But that's kind of a decision for the future adversary to make. So I hope you enjoyed this talk today. I hope what you took away was essentially the logic, the understanding of how to chain the output of commands to the input of others. And I hope that you took that knowledge and kind of saw how it could apply to the real world, where you may be attempting to automate the easier components in offensive security assessments, where you can actually take that learned knowledge, the contextual knowledge, and pass it through the chain in order to create very simplistic, but I guess in some cases like privilege escalation, some more complicated adversary scenarios. And so I hope you learned that this is possible. There are places that automation can come in, solve problems in the red team space, and that you can, as a person on the red team, blue team, purple team, you can leverage this automation in ways to run 24/7 if you want security assessments or off-hour security assessments that are kind of poking at these different areas while you spend the majority of your time working in the more complicated creative areas in the red team space. Thank you very much.